In today's talk, we're going to begin a discussion of the Polya-Redfield method. Here's the basic problem that we're going to be interested in. We already know how to count strings, but what if we want to take a string of letters, say, and wrap it around a circle? Let's say, for example, we want to seat people around a circular table. How many different ways can we do that? Let me show you an example. Let's say we have an alphabet just with the letters A and B. And I have a 3-person table. So I have two types of people, people A and people B. You can think of these as people wearing blue and people wearing green. Men and women, any other pair of things you want. You could seat them around. Let's say, for example, you have 2 A's and 1 B. You could seat them around the table, A, B, A. I claim if you have 2 A's and a B, this is really the only way you can seat the 3 people around the table, because it makes no difference if you write it as B, A. This second method is just a rotation of the first. As far as anybody at the table is concerned, if you're person B, you have people A on your left and on your right. If you're one of the A's, you have an A on one side, a B on the other. So it doesn't matter whether you write it this first way, this second way, or even this third way here, with a B there, and an A there, and an A there. They're all just rotations of each other. We want to consider these the same. Now, of course, they're all different from having 2 B's and 1 A. And of course, these would be different from having 3 A's. Or I won't draw this, 3 B's. We have essentially those 4 different ways of doing things, and all of the other ways of placing A's and B's would be equivalent to one of these two. Let me actually just write them all down here, because I want to talk about this. So here we might have an A, B, B, or here we'll put the A over here with the B, B. These 3, as I said, are equal. We have this one, which is different from the earlier ones, and we have this one here, B, 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 which is clearly different from any of the ones before it. Now you'll notice that there are 2 cubed, or 8 strings, 3-letter strings. And I can associate a string with each of these positions. If I just start, say, looking straight up and go around clockwise, we can think of this first one as the string ABA. We can think of the second one as the string BAA, go from the B to the A to the A. This one would be the string AAB. And those 3 strings would correspond to the same positioning around the table. I won't write these down now, but I'll have BBA is the same as ABB, which is the same as BAB. Here, of course, the string AAA and the string BBB also count as different from the others. So there are 8 different 3-letter strings, but when it comes to how many ways you could arrange people around the table that are now considered different, there are only 4 possibilities. This one, this one, this one, or this one. Is there a way to generalize this, to talk about with tables? What if we have larger tables that can handle n people, and what if we have a larger alphabet? How many ways are there to seat people around the table that are essentially different? And here we'll be more precise. We'll call 2 positionings the same around the table if you can get one from the other by means of a rotation, the way we did here. And of course then, after we've understood how to solve that problem, we'll talk about generalizing it to talk not just about table seatings, but about other types of situations, many different geometric situations where we have different symmetries that would cause us to call 2 positions or 2 strings the same, where they would otherwise be different. So let's first start talking about strings and rotations. We've seen geometrically what we can say about rotations. Let's talk about our string. just a regular old string of letters. Say x1, x2, through x sub n. These could be from any alphabet. This is just an n-letter string. We want to define rotations in the following way. Imagine that you take the string and put it around the table like this. x1, x2, x3, and you keep going around all the way here till you get to xn. And I'm just going to put the arrow here. The x1 is at the head of the table. When we talk about the rotation R1 applied to the string, we mean imagine that we rotate everybody 1 unit counterclockwise. Or equivalently, we just designate the head of the table by rotating this way. This is our new head of the table. We ignore that one. So that the new rotated string will start with x2 and go all the way up to x sub n, but then you have x1 coming at the end. What we'll call R2, R1 will be denoted a rotation by 1 position or 1 unit. R2 is a rotation by 2 positions. That will just be what happens if we, just erase this, change the position of the head of the table here, 1 more spot over. Again, this is like rotating that arrow clockwise, or equivalently, you could imagine leaving the arrow in the same position and rotating all the people at the table counterclockwise. R2 of the original string, x1, x2, through xn, would just be the string that starts with x3, then x4, all the way up to xn, and then we have x1, x2. In general, we can talk about rotation by I units. Here, I will go from 0 to, normally we would say up to n minus 1. I'll show you why in a second. A rotation by I units means we're going to start with xi plus 1. Remember, rotation by 1 unit we started with 2, by 2 units we started with 3. So when we rotate by I units, we'll start with xi plus 1 and go all the way to xn, and then we'll get back to x1, x2, all the way up to x sub I. So that would correspond to, if here's x sub I, and here's x sub I plus 1, a rotation by I units means we're now pointing towards xi plus 1. We're starting here and going up to x sub n, and then continuing with x1 through x sub I. R0 will be an important one. This is the identity. When you apply a rotation by 0 units, that's just the original string, x1, x2 to xn. It doesn't change things. That's why we call it the identity. And if we rotate by n units, we get back to the way we started here. Remember, n is the length of the string. So r sub n is the same as r naught. So how in the world are we going to start to talk about how many different table arrangements there could be, say for n people, when we're talking about a string here of length n? Well, I'll give you an example here when we're talking about strings of length 6. And again, we're going to stick to just a 2-letter alphabet. We'll generalize this into other alphabets later. We know that there are 64, which is of course 2 to the 6th, strings of length 6 from the 2-letter alphabet A, B. But some of them represent table arrangements that are the same as others. To figure out which, we talk about the idea of an orbit. So I've written all, as you can see here on the slide, I've written down all of these 64 different strings of length 6. Let's start with this one, which I'll just use as the first one, AAA, AAB. That's one of those 64 strings. If I apply R1 to it, so this string AAA, ABA is just R1 of the original string AAA, AAB. And then if I apply R1 again, I get this string. In other words, this string AAA, BAA is R2 of the original string. It's R1 of that second string. And then if I apply R1 again, I get AAB, AAA. That's R3 of the original string, R2 of this next string, R1 of that string. And then if I apply a rotation R1 again, I get this string. I apply R1 again, I get this string. And then if I apply R1 to this, I go back all the way to exactly the same string here that I started with. So we have these 6 strings are connected in what we're going to call an orbit. If we just apply rotations, the R1 rotation, we go from this string to this string, 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 and then back to the original one. So these 6 strings are what we call an orbit. We say it's the orbit containing this original string, but you could equally well say it's the orbit containing this string or any of the others. Those strings are all together in the same orbit. Now, if we had started with a totally different string, one which wasn't already included in the earlier orbit, say the string BBB, BBA, and we do the same thing. We apply the rotation R1 to that, and again to get the next one, and again, and again, and again. The last one goes all the way back here when we apply the rotation to the earlier one. Here we get the orbit that contains the string BBB, BBA. Or again, you could just as accurately call it the orbit containing BBB, ABB. They're all in the same orbit. Now, why is this idea of orbit important? Well, when it comes to seating arrangements, let's go back to the first line here. If you have people seated in the pattern AAA, AAB, starting there, that's exactly the same seating arrangement as the one represented by any other string in its orbit. So all 6 of these strings in the orbit represent just a single seating arrangement. And the same is true for strings in this orbit. And then now I've listed all the 64 strings of length 6 from the set AB, from the alphabet AB, by their orbits. If we start with this string, you'll notice this string here, AAAABB, is not one of the ones included in the earlier orbits. We could look at the orbit of that string by applying repeatedly the rotation R1 until we get back where we started. We see there's an orbit of length 6 that contains this string. Well, do all the orbits have length 6? No. We'll see the orbit for this string here, BBBBAA, is of length 6. So is the orbit for AAABAB. Same thing for the orbit BBBABA. But now look at this string, AABAAB. When I rotate that by 1 unit, apply R1 to that, I get ABAABA. I rotate it again by 1 unit, I get BAABAA. But then I rotate by 1 more unit, I get back where I started. This is an orbit of length 3. And the similar thing is true for BBA, BBA. You'll notice this is just the same string as that with the A's and the B's. The B's replacing A's and A's replacing B's. So sometimes orbits have length 6, sometimes orbits have length 3. Here we see some more orbits of length 6. But then we get here an orbit of length 2. Look at this string AB, AB, AB. When you rotate it once, you get BA, BA, BA. You rotate it one more time, you get back to AB, AB, AB. This is an orbit of length 2. And then, of course, it should be pretty obvious we have these 2 very simple strings, AAA, AAA, with the orbits of length 1. You just apply any rotation to that, it stays the same. And the same for BBB, BBB. So if we're going to ask the question, how many different ways are there to seat people of 2 different varieties, type A and type B, around a table, where we consider 2 table seatings the same if you can get to one from the other by a rotation, That's the same as counting these orbits, and you'll see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 different orbits among these 64 strings, and you can partition this set of 64 strings into these 14 orbits, and thus we'd say there are 14 distinct seating arrangements. The question we're going to be working on for the next 2 weeks is, how can we generalize this? How can we answer the question for any size strings from the 2-letter alphabet AB or from any other alphabet? And of course, then how can we generalize it to other geometric configurations that aren't just sitting around a circle?